Okay, so thank you very much for the invitation. The talk will not be about statistics, as you see, but actually it has very little to do with statistics. But I will start with the connection to statistics, and then I will come to the, say, algebraic side, and the main part of the talk will be about the algebraic results on these rank 1 generated spectrahedral cones. Das geht nicht. Okay, so the class of problems which is considered are so-called quadratically constrained quadratic programs. So this is a very general class of programs, and it consists of minimizing a quadratic function with respect to quadratic constraints. So we the pointer would be nice, but, yeah, the mouse is better. Yeah. Okay, so we have a cost function, which is, I see it, yes.
Better because everybody can see it on the screen.
Okay, so we have a cost function, which is defined by n times n symmetric matrix. We have a number of matrices AI, which define homogeneous quadratic constraints. And we have a matrix B, which defines an inhomogeneous quadratic constraint. So this is not a restriction of generality. If you have general quadratic constraints, then you can always pass to one inhomogeneous one, and all the other ones are homogeneous. And we can rewrite this problem. Now it's in the space Rn. We can rewrite it in terms of a matrix variable. So we take a big matrix X, which is a rank 1 matrix combined of the decision variable small x. And then these quadratic expressions here become linear in this matrix variable. But now we have a rank constraint. So the linear constraints are easy, but the rank constraint is what makes the problem difficult. And actually, the general problem is NP hard, so it's hopeless to solve the general problem. But we can look at approximations, and the approximation which will be applicable here is just dropping the difficult rank constraint and consider a linear program over the matrix decision variable. Okay, so we can still rewrite this problem a bit. So we put all the homogeneous constraints together and define a linear subspace of the real symmetric matrices, which fulfill the homogeneous constraints. And then we have an optimization problem over this subspace with a rank constraint and an affine constraint. And the set of positive semi-definite matrices, which is in some linear subspace, is called a spectrahedral cone. So it's essentially, it becomes a conic problem over a spectrahedral cone with a rank constraint. Okay, and we relax it just by dropping this rank constraint, and then we get an optimization problem over the spectrahedral cone with just an affine constraint, which can be solved with standard means. So it's nearly 20 years that this class of problems is efficiently solvable, and the solvers are now ripe enough to make it.
Sorry, what are these angle brackets?
It's just a scalar product in the metric space. So it's AB is just a trace of A times B. So it's a sum over all elements and element-wise product. So actually then we get x s is equal to xxt s, and this is equal to xt s x. So this is how it arises. And then we can ask under which conditions this relaxation is exact. So when does the relaxation not harm the result of the optimization problem? And an obvious sufficient condition for that is that the extreme rays of these spectrahedral cones are actually rank 1 matrices. So we know if we optimize a linear function over a convex set, then the optimum will be in an extreme point. So if the spectrahedral cone is actually generated by rank 1 matrices, then we will always get the right result. So we make a definition, and we say that a spectrahedral cone whose extreme rays are all rank 1 is rank 1 generated. So this class of spectrahedral cones, which are nice for the solution of the quadratically constrained quadratic problem, will be the subject of the talk. And actually this class of problems is very large and has many applications, not only in statistics, but this is just a list. So, and you can see that it's widely used. And also the relaxation, which consists in dropping the rank constraint, is actually the canonical way to approach this kind of problems. So in all these papers which you see here, actually the solution method which is proposed in these papers consists of formulating this quadratically constrained quadratic problem and solving it by a semi-definite solver when the rank constraint is dropped. Okay, so let us look at some examples of this class of favorable cones. So at the simplest example is, of course, the full matrix cone. So we know that the extreme rays of the cone of positive semi-definite matrices are exactly the rank 1 matrices. So this is a rank 1 generated cone. And there are also non-trivial examples. So it's well known that the Hankel matrices, the positive semi-definite Hankel matrices, are generated by the rank 1 Hankel matrices. And this implies that, or is equivalent to the fact that any univariate polynomial which is non-negative is also a sum of squares. So it's a classical result. And we have also the tri-diagonal matrices. So these are matrices that have something on the diagonal and on the two diagonals which are next to it. And here is 0. So the cone of tri-diagonal matrices which are positive semi-definite is also generated by the rank 1 matrices of this kind. And then we have this exceptional example of a 15-dimensional cone in the space of 6 times 6 matrices. And it's essentially a result of Hilbert from the 19th century that this is a rank 1 generated cone. So this is just equivalent to the fact that homogeneous polynomials of degree 4 in 3 variables are sum of squares if they are non-negative. And we will see in the course of the talk, actually, that one can construct a lot of other examples of such cones. And so the class of these favorable cones is actually not that small. So at first, we can give an algebraic characterization. So from real algebraic geometry, in real algebraic geometry, we have an object that's called an algebraic interior. So what does it mean? If we have a polynomial, an Rn, and consider the connected components of the set where the polynomial is positive, then the closure of each of the connected components is called an algebraic interior. And obviously, any spectrahedral cone is such an algebraic interior. But not in any spectrahedral cone, the determinant of the matrices is the minimal polynomial, which defines the algebraic interior. So any algebraic interior can have different polynomials which define it by their components of positive points. But there is essentially one minimal. And for the rank 1 generated spectrahedral cones, the determinantal polynomial will always be the minimal one. So this is an important point which these cones fulfill. But they are actually not the only ones that fulfill this condition. Okay, so by the degree of this polynomial, we can define a degree of the cone. And then we see that this degree has connections with other properties of the matrices in the cone. So the degree of the cone is always equal to the maximal rank. That is clear from, because just the determinant of a k times k matrix is of degree k. And there are also connections to representability of interior points by by convex combinations of extreme points. So in a rank 1 generated cone, if we pick a matrix from inside and it has rank m or small k, then we may find k extreme elements such that the sum of these extreme elements is equal to the given matrix. So this is not valid for general spectrahedral cones, but it's valid for these rank 1 generated ones. Okay. Yeah, actually, there's a line that is. Oh, but you can see the last line. So that essentially means that no. Okay. Yes. Now we can we look at isomorphisms, and first we shall define isomorphisms of general spectrahedral cones. So if we have a linear subspace L in the space of n times n symmetric matrices, and consider the cone of all matrices in L which are positive semi-definite, then on the one hand, it's a spectrohedral cone which consists of matrices, but on the other hand, one can look at it just as an abstract convex cone in a real space. And then it turns out that actually the structure of the cone as an abstract convex cone does not determine the structure as a spectrohedral cone. So, and for this we can look at this example here. So if we take the orthant in R2, we can represent it in different ways as the intersection of the cone of positive semi-definite matrices with the linear subspace. So we can take, for instance, the cone of 2 times 2 positive semi-definite matrices intersected with the diagonal matrices, and then we get the orthant. Or we can take the, for instance, the cone of 3 times 3 positive semi-definite matrices and intersect it with this subspace. So we also get the orthant, but obviously these two representations have very different properties. So for instance, the extreme rays here have rank 1, and the extreme rays here have rank 2. The interior here is of rank 3, and here it's of rank 2. So these representations of this abstract cone, the positive orthant, are obviously different. And for rank 1 generated cones, it appears that this cannot happen. So if we have a rank 1 generated cone and consider it just as an abstract cone in a real vector space, then all its representations as rank 1 generated spectrohedral cones are isomorphic, where the isomorphism is of this form here. So if we have a matrix representation in one space, then we can pass to any other matrix representation in another space by such a linear transformation with a fixed coefficient matrix A. So this is actually a very strong condition, and it has a lot of consequences. Okay, so now we pass to an attempt to classify these rank 1 generated cones. And the first thing that one can attempt is to define what is a simple cone. So in the theory of, for instance, Lie algebras or Jordan algebras or whatever, an object is simple if it cannot be decomposed as a direct product of smaller objects. And we can do the same thing here. And the basis of this possibility to do this is that if we have a cone which is a direct product of other cones, then it's a rank 1 generated spectrohedral cone if and only if all these factor cones are also rank 1 generated spectrohedral cones. So this is a non-trivial condition, a non-trivial fact, and it allows one to distinguish simple cones which are not decomposable and products which decompose in simple cones. And since the decomposition of a convex cone into factors just as an abstract set is unique up to permutation, this will also be true for the rank 1 generated spectrohedral cones. So we may essentially restrict ourselves to the study of simple cones. Now we will look at ways to construct such simple cones. And one simple or easy possibility is if we have a cone of, say, size n times n. So this is a subset of the cone of n times n positive semi-definite matrices. And we take n prime bigger than n, then we can construct a cone n prime in the cone of n prime times n prime, symmetric matrices in the following way. So y is in K prime if and only if we can express it in block decomposed form as follows. So in the 1-1 block, which is of size n, we have an element of the original cone, and here we have whatever we want. So this is essentially another spectrahedral cone, and it turns out that it is rank 1 generated if and only if the original smaller cone is rank 1 generated. So we may call this a full extension of a spectrahedral cone, of a rank 1 generated spectrahedral cone. And we can also characterize when a given cone is a full extension of a smaller cone, namely if and only if this condition here is fulfilled. So if the cone is the intersection of some linear subspace with the positive semi-indefinite matrix cone, such that the subspace contains matrices of this form, where these are rank 2 matrices, where each vector y is arbitrary and x is in some given non-trivial linear subspace. And it's also to be seen that such cones here, whatever this is, are simple. So even if this is a product, so this will be a simple cone. So we see that already the class is not that small, but there exist much more general constructions which allow us to construct new rank 1 generated cones from given ones. And this happens essentially in the following way. So let cones K1 and K2 be given, where x1 in K1 is partitioned in some way in 2 times 2 blocks, and x2 also. And assume that matrices of the form 0, 0, 0, and here anything you want, which is positive semi-indefinite, is in K1, and matrices of the form like this are in K2. So this is in K1, this is in K2. And then we may construct a new cone, which is partitioned in 9 blocks, where this here is in K1, and this block here, this is in K1, and this is in K2. And then it appears that this large cone is rank 1 generated if and only if the small cones are. So this is a non-trivial construction, and it actually allows to construct a lot of rank 1 generated cones, and among them also the tridiagonal matrices. So how does it work for the tridiagonal matrices? It's probably a good example to demonstrate. So first we take a 2 times 2 matrix, and any matrix whose 2-2 block is filled and everything else is 0 is obviously tridiagonal. And then we apply this construction to this cone and to this cone of 2 times 2 matrices, and then we add this one and so on until the end. And then by this result we obtain that this space of tridiagonal matrices must be a rank 1 generated cone. Okay, so we may do it So this central block is not necessarily 1 times 1. It can have any dimension. So this is a more complicated example where we have taken 5 such subspaces of rank 2 matrices, but combined them in a much more non-trivial way. And by varying the way we combine them, so we have here 4 parameters, and each choice of these parameters gives us some cone, and all these cones are rank 1 generated, and moreover they are in general non-isomorphic, so it's essentially a one parametric family of cones. So we see that already for the size 6 times 6, the class is already quite large. Okay, so if we consider the relation between the dimension of the cone and the degree, we can construct other subclasses of such cones. So for instance, by Dinier's theorem, we know that any spectrahedral cone, general spectrahedral cone, which has codimension 1, must be rank 1 generated. And for codimension 2, there are very little such cones, so any such cone must be a full extension of a cone in dimension 3 times 3, which has these 5 elements filled, and here 0s. So any cone of 2 dimensions has to look like this, essentially, of codimension 2. And on the lower end of the dimensions, there exist also bounds. So a simple cone, which is rank 1 generated and has degree n, must have dimension at least 2n minus 1. So this is the least dimension that can be realized for simple cones. And examples are, for instance, the Henkel matrices or the tridiagonal matrices. Okay, so now time's up. So I will skip this. And this is a classification of matrix sizes up to 4. It can still be done. For 5, it gets already more complicated. Okay, so thank you very much.
Some questions?
So you just broke this rank constraint. Usually it's just relaxed by the trace constraint. What is the definition of
The trace constraint actually is not so that you have this constraint here, the inhomogeneous one, and this just becomes the trace constraint. So the B is just the identity matrix. So what is dropped is the rank constraint. The trace constraint remains as it is.
Thank you.